students in attendance will maybe be interested to know that today's speaker was a student here and actually took a course from me, and I just discovered I'm a co-author with him. That may seem impossible, like how could I just discover that? I taught a course in compressed sensing some years ago in which all the students submitted data, and then the course TA, Hatef Monajemi, and I wrote it up, and we had a paper in Proceedings of National Academy of Sciences based on all the data. And it had, dozens and dozens of co-authors because of all the people who contributed data. And so I've forgotten all of their names. They're written down at the PNAS website, but apparently Andrew's one of them. He has many more distinguished achievements than that. First of all, he's very recently a newly minted assistant professor at Oxford University. It's fascinating to me that he's in a department of experimental psychology. Most of the people who are doing the kind of deep learning work that we've been talking about are in some way associated with computer science or electrical engineering or physics, and experimental psychology seems to be a reach. But you'll see that he's written a number of papers that have become pretty prominent, and I recognize his name from a number of highly cited papers in deep learning that he's done. I'll mention just a couple other things. He's at Oxford, but he's not teaching right now, so he's not doing the beginning experience of teaching Oxford undergraduates how to do their calculus courses. Instead, he's very well funded because of all his research achievements, and the only Oxford experience that he seems to have additional information about is the ample supply of wine in the college that his wife is, I guess, a member of, or whatever is the appropriate word. In any event, we welcome him here to tell us about the use of the linear case as a bootstrap for understanding high-dimensional learning in deep nets.
Thank you. Okay, so what I'm going to talk about today is, as you'll see, an extremely simplified case. It's a simple form of a deep network. And I think there's real value to studying simple toy models. It's a philosophy that you might have seen if you've interacted with physicists. You approximate a cow as a spear. That's kind of the way that we're thinking about deep networks. But still, you'll see that I think this simple model is quite interesting and can get you into some conceptual insight into what's going on. So the key puzzle that I'm interested in is understanding sort of all of the features that are going into current practice in deep learning, understanding how these networks work. And we know that they work very well. And I think that the standard tale about them goes something like this. The benefit of depth is that you can compactly represent complex functions. And then the drawback of depth is that deep learning is hard in some sense. Slow, difficult, doesn't always converge, something like this. And I'm not going to talk about that issue of representing complex functions, but I will spend a lot of time on what might be making deep learning hard and the exact dynamics that go on here. And so just as a simple example, here's a 5-layer network. It's learning to recognize handwritten digits. And you can see that it starts off with some training error and apparently does nothing at all for the first 150 epochs before it starts getting better. And the trajectory is quite nonlinear. So we'd like to understand that whole trajectory and why that occurs. And I won't really talk about this, but my motivation also is very neural and coming from psychology. So for instance, it is just the fact that the brain has this layered anatomy as well. So your visual cortex goes through a number of stages. And we'd like to understand how that layered anatomy is impacting learning dynamics. Also, if you zoom into any one layer, there's sublaminar structure within each area. So there is actually a lot of sequential stages of processing in your visual stream. And so somehow the brain has to be approaching this deep learning problem as well. So what I'll talk about today is an attempt to really isolate what depth is doing to the learning dynamics as opposed to other features of the learning setup. And then I'll talk a bit about generalization as well at the end. So there's sort of three parts. First, training dynamics. Then I'll talk about scaling laws. So as you make a network deeper, how do you expect training time to change? And finally, I'll talk about generalization. And the class of model I'm going to use is this deep linear neural network. And again, just to motivate why it's, I think, interesting to study a simple model is we're always talking about how deep networks are black boxes, right? If we're going to have any hope of penetrating that, maybe we should start with a simple model that gives you conceptual clarity about what's going on and very clear predictions that you could take to test in experiments if you're interested in the neuroscience side. All right, so what is this deep linear network? Well, here's your standard deep network. So you have inputs, you apply weight matrices, these nonlinear functions f, and basically the barrier to making easy theoretical statements about these networks is simply these nonlinearities. So you can do something very drastic and just take them all out. So we've just knocked out all nonlinearities, and all this network's going to do is just multiply a bunch of weight matrices together and try to produce an output. And at this point, you're probably thinking, well, hold on a minute, surely that's trivial, because the input-output map is always linear. So if I have an input x, then I'm just taking a product of a bunch of weight matrices to get my output y hat. But I could have just implemented that with a single weight matrix, implementing the total input-output map, because the composition of linear maps is linear. So you're gaining nothing in terms of representational power from adding these additional layers. So you can do that as a downside. You can also reframe it as a positive by saying we're controlling for representational power, right? And all we're doing is asking how the depth itself, this factorization into layers, changes the learning process. And just to show you that these can do some surprising things, here, actually that training trace I showed you from earlier was a deep linear network. So it shows these long plateaus with sudden transitions. And these networks also show canonical phenomena, at least from the early era of deep learning, where people were very excited about unsupervised pre-training. So here's a network where we did some unsupervised learning for a while, and then we trained it on the task of interest, and you see it trains much faster. So these are the sorts of phenomena that hopefully we can understand in this linear case. And I just want to make it very clear why this model is giving this rich behavior. So when I say it's a linear neural network, what I'm talking about is the map from the input x to the output y hat. That is simple and linear. And then you're going to take that and you're going to plug it in to an error function. Right? And that error function is, here I'll be taking this as squared error. And that's where the nonlinearity comes back in. And then learning is minimizing that loss with respect to the different weight matrices. And as long as you have one or more hidden layers, this optimization problem is non-convex. So it has this key property of the nonlinear setting that the optimization is in fact non-convex. And so this is basically saying that you can have models at all these different points of complexity. They can be shallow or deep. They can be nonlinear or linear. So we're all familiar with linear regression. That would be a linear shallow case. A nonlinear model can also be shallow, like support vector machines. There you know that learning is going to proceed well. And then deep networks, of course, over on this corner, where they're nonlinear and deep, and we're just filling in this extra point here. And the interesting thing is that in terms of representational power, things split along this axis, right? So if you're trying to solve a problem like an XOR problem, the linear models will all fail, regardless of whether they're shallow or deep, but the nonlinear ones will all succeed, regardless of whether they're shallow or deep. But the learning dynamics split the other way, right? So in the shallow network, it doesn't matter if it's linear or nonlinear, you can formulate things, you get nice convex learning. But in the deep network, it's convex, non-convex in both cases. Okay, so the goal here is to sort of understand these dynamics. So here's what happens if you just write down the gradient descent equations. And I won't spend too much time on the details here, other than just to note that the weights show up in up to cubic interactions, right? So the products of the weights show up repeatedly in these equations. That's what's making them intricate and interesting. And that means there's coupling between layers. So to know how to change the weight of layer 5, I need to know all the other weight matrices in the network. They're all coupled together. And another important fact is that the only way that the data set enters the picture is through the input correlations and the input-output correlations. This is only true for these deep linear networks, but these two matrices fully summarize everything you need to know about the statistics of the environment. And so what we like to do is understand how these dynamics unfold as a function of the environmental statistics. And these models are, of course, not new, so there's been lots of work going back many years. The critical points were worked out. Some aspects of the shallow dynamics have been worked out. The main thing that I'm going to add here is an analysis that applies to very deep networks. All right, so how can we make progress in analyzing these networks? The idea is to use a very particular change of variables in which the dynamics simplify. So let me explain how this change of variables works. Across the top here, I have the statistics that the world is giving me. Here I've just hand-drawn a specific example. So I have 4 items, a bird, a fish, a tree, a flower. And then I have a bunch of properties that they have, which are the outputs here. So all of the items can grow, some of them can move, and then they all have these individuating ones. So this is the statistics that come from the environment. And now I'm going to decompose that into the product of 3 matrices using the singular value decomposition. And the singular value decomposition is going to break this matrix down into the product of several modes, right? So one mode will link a column of these features here to a row of this matrix here, and it's saying what features are common to the items that are picked out by this row. So this row is positive across all of the items, and the feature that it has the strongest weight to is that they all can grow. And the next level, you can see it picks out the next level of the hierarchy, and that distinguishes the feature move from the feature has roots, and so on down the tree. And then the strength of that association for each of these modes is determined by this singular value along the diagonal. So that's just a way that you can decompose the environmental statistics. And it turns out that if you look at the network in this frame of reference, then the dynamics become particularly simple. So here's how that works. You have your neural network. It's basically going to do a change of variables. So I put in this U matrix, put in this V matrix. And then it's going to have effective singular values along the diagonal. It will start off at 0 when it knows nothing, and then it'll increase over time to their final values. So what this is saying is that the linear network is going to do a time-dependent SPD, where the singular values change over the course of learning. And just to go very briefly into some of the technical content here, what this change of variables is doing is decoupling the network. So in the original network, it had all of these weights coupled together. It wasn't clear how things would change. The SPD change of variables separates them out into these independent 1D chains. And you really can think of it as what would happen if you just had a chain of single neurons. And the important simplification is you don't need to know about any of the other chains to figure out the dynamics for one of them. Okay, so let's just zoom into one of these chains. What it's going to do is take an input, project it onto the associated input singular vector, multiply it by a bunch of scalars, and then that will determine the projection of the output onto the associated output singular vector. And the overall product of these effective layer weights is the effective singular value. Right, so it's just the product of these individual layers. And this is the quantity that we can use to track the learning dynamics in a straightforward way. So here's sort of an example of how this all comes together. I'm starting the network off with no knowledge. And you can see over time, these effective singular values pop up until they finally reach their final values, at which point the network is producing the same statistics as was given to it. Okay, so now we can drill in a little more detail to understand the dynamics of this learning process. What I want to show you is the error surface coming from just one of these 1D chains. So what's happening to one of these effective singular values? Well, it has this simple error surface. And if I take another technical assumption, if I assume that the way you initialize the network is with roughly balanced layer strengths, then I can in fact plot for you what the error surface looks like as a function of that layer strength. So here's an example. The network's supposed, it gets 1 as an input, it's supposed to produce a 2, essentially. That's it. This is completely simple 1D chain right here. And I'm just plotting what the error surface looks like as a function of this layer weight B, which I assume is the same in all layers, as a function of the network depth. And what you can see is that indeed for a shallow network, if you have no hidden layers, it's just this nice simple bowl. But now once I start adding depth, the error surface changes dramatically. You have this plateau here. And the plateau gets longer as depth increases. And so it's always the case here that you have global minima for all of these different depths. There's no real way things can get stuck except for this saddle point sitting at the origin. Okay? If you started right with an initial weight of 0, learning dynamics would stay there forever. But the way things that are really slowing down in training dynamics is actually from this plateau, which is right next to the saddle point.
I have a question. So
Yeah.
you had an equation where you took the input data, you multiplied by some singular vectors, right? And then you at the end multiply by more singular vectors, and in the middle you multiply by a bunch of singular values. What happened to the intermediate singular vectors between the layers?
Yeah, they basically don't end up mattering, because basically the singular vectors in one layer will be the transpose of the singular vectors in the next layer, and so they cancel out. And so it's just saying that the information is fully transmitted in these.
So is this like an RNN hypothesis or something? Is that?
It's not. It could be an RNN hypothesis, yeah, but it is the solution that emerges if you train from small weights. Yeah.
If you train long enough, the singular vectors correlate with each other perfectly, right? That's what you're saying?
Yeah, and right, yeah. So there's this very brief, so there are technical assumptions I haven't discussed. So the biggest one is that the dynamics I'm going to show you assume that these off-diagonal elements start off to be equal to 0. There's no reason they have to, but as an empirical observation, they rapidly do go to 0 if you start them from small values. So that's basically saying that they do rapidly decouple if they start off overlapping. Okay. So if I plot the training dynamics coming from just one of these 1D chains, I start them off at different points on this plateau, and you can see that under gradient training, the plateaus really slow things down, and so the deeper networks take much longer to expel. And they will learn eventually, but it takes them much longer. And the nice thing about having these differential equations is that actually you can solve them for different depths. So here I just pull out 3. This is shallow network. You just get exponential approach. The deep network starts to look sigmoidal, and this is what happens with a very deep network. And I'll just plot these functions for you so that you get a sense of what they look like. This is, I think, one of the essential ingredients that depth adds to the dynamics. If you look at the shallow network, it just does exponential approach to the asymptotic singular value that it's aiming for. Whereas in the deep network, you get this qualitative shift to a sigmoidal trajectory. This is long period where apparently no learning happens. You're stuck near that plateau, and eventually you expel off it. And in very deep networks, it's still sigmoidal. It's just you sort of take longer to get off the ground. So at least in deep linear networks, the big difference is, do you have any hidden layers or none at all?
So is it like the A of one of the lower pictures is like the higher pictures A to a power, and it just takes longer to get away from 0 if I'm squaring or cubing or something?
Yeah, that's it. I mean, there's lots of different names for the same phenomenon. You could also call it vanishing gradients. I mean, just imagine taking this B. If B is 0.1, then 0.1 times 0.1 times 0.1 times 0.1 is a very small value at the output. That's really all that's going. Yeah. Okay, and then that was coming from one mode, but again, they evolved independently. So if you have lots of them, then they just come up together according to each of their trajectories. And so in the shallow network, what you get is this time-dependent SVD where things are exponential approaching, whereas in the deep network, they're strongly staged in time, and they have this sigmoidal structure. The red curves here are showing what happens if you simulate these networks from small random weights. Okay, so because you have these explicit solutions, you can ask all kinds of questions about these dynamics. One very simple question is, how long does it take to learn a particular dimension of the data set? And the answer is very straightforward. For the deep network, it scales as 1 over the singular value. So that's just saying that very straightforward idea that the stronger the statistical association, the faster you learn it. But the interesting thing is, in fact, the shallow network, it goes as the log of the singular value. Right? So what that's saying is that if you look in this plot, these different sigmoidal trajectories are strongly staged in time. There's a big gap between them. Whereas all of these are coming up more or less at the same time, even though they're aimed at different singular values. Okay. So that's sort of a brief picture of training dynamics in these models. And now we can look into this question of scaling laws. So the idea here is, suppose I took a network that's 10 layers deep, and now I make it 20 layers deep. How would you expect it to change in terms of its training speed? And the result that emerges from these linear networks is very straightforward. It just says that the time scale for a very deep network, as compared to a shallow network, scales as 1 over this initial effective singular value strength raised to the power of the depth of the network. Okay? So here, V naught is the strength of the weights in one of those 1D chains in one layer. And if you think about if this is a small number, then a small number raised to the power of d, you're going to learn exponentially slowly in depth. Whereas if you were able to get this parameter to be near 1, and 1 to the d is still 1, then training would be fast. So this makes the basic prediction that deep learning speed depends exquisitely on the initial conditions you use. And just some examples of that. So I think when people first started training these deep networks, this is the regime they were in. If you just go back to those papers, the initial papers, they would always initialize with weights from very small values, and they saw terrible scaling of training speed with the depth of the networks. And then the big breakthrough from Jeffrey Hinton in 2006 was this pre-training strategy. If you look into that in more detail, what it does is it sets these initial layer strengths to be equal to approximately 1. And then training proceeds quickly, except that you had to do these D pre-training episodes, so you scale linearly with it. And finally, this suggests, at least in the deep linear case, that if all you care about is training speed, you can get depth-independent training times just by explicitly setting your initial weights to have singular values of 1. So that corresponds to the orthogonal initialization, which can fully fix things in the linear case. So here's just an empirical example. This is done for MNIST for lots of different.
Just for Jeff Pennington spoke a little bit about orthogonal and nearly orthogonal cases a few weeks ago. So some students might remember that.
Yeah. Yeah. So that work arrives at very similar suggestions to what I'm about to show you, and I think was done, building from these concepts. Yeah. So here, for instance, as I scale the depth of the network, I'm looking at the time it takes to reach some criteria of accuracy. You can see it does increase, but it saturates. So it's not like these deep networks are doing very poorly. And in fact, if you compare these different pre-training strategies, then indeed the orthogonal method has essentially depth-independent training times. Jeffrey probably also showed you similar results, but with nonlinear networks. And the idea can be generalized to the nonlinear case. So here, for instance, in these red curves, what happens if you're initializing with orthogonal weights that are scaled appropriately to account for the nonlinearity? You can see that they really dramatically beat the training speed of these the standard best practice initializations, and this is true even for very extreme depths. So here's a depth 100 network training in basically the same amount of time as a depth 10 network, if you initialize it correctly. Okay, and one other sort of footnote to this story is there's two pieces to this initialization suggestion. One is scaling the weights so that the the activity successfully propagates through the network. And the other is this notion of orthogonality. If you have to choose only one, you should definitely focus on scaling. The scaling is what matters, is pushing you away from that saddle point. The orthogonality is less crucial. And so here, for instance, I'm showing you the Turing criterion for random networks versus orthogonal networks. They're still pretty good even if you just do scaling to the random networks. I don't think the orthogonality is super crucial here. Okay, so to summarize the picture emerging from training dynamics, I think it's quite interesting that really depth alone, just factoring that weight matrix into the product of a bunch of weight matrices, changes the dynamics of gradient learning. And the key effect I showed you was these sigmoidal transitions in the training loss. And I think that's sort of a key feature of depth. And I've also suggested that the way you initialize these networks is critical in affecting their training speed. And I think there's a lot more to be said about different types of initialization. So I've really only talked about the simplest ones. There's lots of caveats here. So I've only talked about training error. There's some nice work looking at generalization error. And there are technical assumptions being used here. So the solutions that I'm showing you are approximate. They describe what you get if you start from small random weights. But if you don't, you can see something very different. Okay, so now let's turn to the question of generalization. Of course, generalization is actually what you care about when you design a machine learning system. And that is something that we would like to understand. In particular, how does generalization depend on initialization? Or how long you train? Or the statistics of the data set? Or the complexity of the model, right? And the observation, which I'm sure you've heard probably many times in this course so far, coming from practitioners, is that apparently bigger is better. Right? So here's an image network. I think each one of these blocks can itself be several neural network layers. This is a giant network with tons of parameters, and it was still the best performing network on ImageNet at the time. And if you look at this more systematically, here, this plot is showing generalization accuracy on ImageNet on the y-axis. The x-axis you don't have to worry about, it's computational operations. But then the circle, the size of the circle is the number of parameters in these models. And so you can see that these absolutely huge models, 155 million parameters, they're still doing pretty well in terms of accuracy, even though they're being trained on only 1.2 million examples. So the ratio of the number of examples to parameters is very small. So again, my approach is going to be to just carve this down into the simplest setting you could think about. So just sort of to fix the principles that are going on here, let me start off with this very simple example. Suppose you're fitting a sinusoid. You've probably seen this in machine learning textbook. You're fitting a sinusoid, and I'm just going to give you these circles. So 10 of these circles. And I'm going to fit it with this little neural network. So it has rectified linear nonlinearities. It receives a scalar as its input. And to keep things extremely simple, I'm going to randomize this first layer and just learn this second layer. All right? Start off the weights at 0, train with gradient descent, and off we go. So if I just have 2 hidden neurons in that network, then it can't do well. It can't even fit the training data. It's not going to generalize well. And this is sort of the beginning of the standard morality tale behind generalization in machine learning. Is, if your model's too simple, you just can't even fit your training data. Then there's this intermediate regime where things are looking pretty good. And of course, if you go to more complex models, things just get completely crazy. All right. So this is the standard trade-off between bias and variance. But you'll notice that these plots never show you what happens if you just keep going. And so I'm going to change nothing about the setting, but instead of 10 hidden neurons, I'm going to go to 500. And all of a sudden, it just works beautifully. So you can see that this is, in fact, the best model that we trained. It has the best MSE error, and it's essentially right on top of the target function. So if you're sort of more systematic about this, what you find is this spike in training error at an intermediate model size, and then things get better whether you go smaller or larger from that point. Okay, so a lot of people have pointed to this as a puzzle, and I just, at a high level, want to say that this was a puzzle in the past as well. And I think really you probably already have the intuition, which is the way out of this puzzle. And that is, if you consider a support vector machine, you're not worried about whether that's going to generalize well, even if you use a kernel that corresponds to an infinite number of features. Right? So if you use an RBF kernel, you're training a model with infinite features, but you're not worried about its generalization performance. That's because it was regularized by finding the maximum margin solution. And the generalization is guaranteed by the size of the margin you find. All right? So I think the same picture happens in neural networks. We know that the norm of the neural network's weights bounds the complexity of the function it can represent. And so again, if you can regularize the norm of those weights, then you would be justified in thinking you generalize. So if there is a puzzle, it's really this question. It's where is the regularization coming from in the typical training procedure that we use in neural networks? And I just want to say that you might have heard of, so a lot of proposals say, well, it comes from SPD. It's the stochasticity in SPD. But the results that I showed you were for pure batch gradient descent. So even with pure batch gradient descent, things go fine. You might also have thought, well, but you don't really train forever. Maybe it's just early stopping. But the results I showed you were for training for very long times. And this happens, in fact, with infinite training times. It's not that either. So where is the regularization coming from? So to get at this, I'm going to take a very simple model. I'm going to have a teacher neural network that will provide student examples to the student network. So here the teacher has this input vector of a bunch of inputs, and each of these elements will just be drawn from random Gaussian. And the weights of this teacher network will also be drawn from random Gaussian and then fixed. And that will provide a label. And then we add some noise. And then this is now a labeled pair of an output and associated input that we can now provide to our student, which will have to learn this simple task. So again, we're studying linear regression. We're learning a random linear regression. But we'll see that it preserves interesting features of the overall problem. Okay, so we can use this model to sample P examples. So we're just studying this very simple linear model. And we're going to be interested in the high-dimensional setting. And by that I mean that the number of examples relative to the number of parameters is going to be a finite ratio. And we're going to take each of P and N going to infinity for the purposes of analysis. All right? So the virtue of doing that is we can study the regime where you actually have fewer samples than the number of parameters and start to get some insight into that case. And there's a ton that's known about this regime again. Lots of results here. In fact, I think pretty much everything I'm going to tell you was already discovered long ago, but I think it's relevant for today, so it's worth knowing that. All right, so what are we interested in measuring? Well, in this setting, we can compute the training error on the exact data set that we're giving to the network, but we can also compute the test error. And this is the error on a new example pushed through the teacher. And this is why we needed the teachers, because we needed a model of how the data was generated to be able to calculate the true test error. Right? So we made a strong assumption about the data generation model, and this was the payoff, is I can analytically calculate what the test error is as a function of the student's weights. So in the setting now, we can analyze how the training dynamics proceed. And this is just what the gradient descent dynamics look like. The weight change, again, this is a shallow linear network. It's just given by this equation, starting from these initial conditions. And because it's linear regression, we know where we're headed. You're headed to the least squares solution, right? So the fixed point is going to be at the least squares solution, plus possibly a contribution from parts of the weights that are orthogonal to the input data if you're in an over-parameterized model. But we're really interested in the full trajectory you take, not just where you wind up, but the full trajectory. So again, the approach is similar to what I talked about in the first section. We just need the right change of variables. Here it's very simple. It's a linear system. We're just going to change variables based on eigendecomposition of the input correlation matrix. Right? So this is just PCA on your input data. And we're going to look at the dynamics in those principal axes. And with this change of variables, then if you sort of push that through, what you get is, again, decoupled modes. So that's the payoff for the change of variables. Right now we have these new variables z. You don't need to know what all the other z's are doing to know how any one of them is changing. And the dynamics are now expressed in terms of the eigenvalues of this covariance matrix of inputs. And because this is a simple linear system, we can solve it and then interpret the solution that comes out. So here's sort of the broad picture of what the solution looks like. It has these two different components. The first term says, forget your initialization. So it's exponential decay, and the time scale is related to the associated eigenvalue of that input mode, and it's decaying away to 0. The second term is exponential approach, starting at 0 and increasing to 1, and that you can interpret as overfitting to noise in the data set. Right. And there are a few things to note about this equation. First of all, the time to learn each mode depends on the eigenvalue, so it's in the exponentials here. And also, that eigenvalue appears in the denominator of this overfitting term. So what that means is if you have a very small eigenvalue, which remember is just the variance of the input data in a certain direction. So if you have a direction of your input where you have very low variance, then you're going to overfit extremely badly. Right? So the small values here are what really bad. And then the final thing just to note is what happens if you have an exact 0? Well, then you're just stuck at your initialization. There's going to be no dynamics. Whatever you had initialized to, you will stay there forever in that particular direction. Okay, so in order to understand whether a particular model will overfit and how badly it will overfit, what we need to do is understand what the typical distribution of these eigenvalues would be. Right? Because if you have lots of small ones, then we'd expect substantial overtraining, and things could be very bad initially. If we have lots of large ones, then you have little overtraining, things will be fine. And if you have some exact zeros, well, it's not going to lead to overtraining, but it is going to be a constant error, because you never learn those directions. So what is the typical distribution of these eigenvalues? Well, again, as we made strong assumptions about the data, this distribution is well known from random matrix theory, and it has the following structure. So this is called the Marsenko-Pasteur distribution, and it depends on the amount of data you have. So remember, alpha is the ratio of the number of examples to parameters. So that comes into this process. And what the distribution looks like is it essentially has this bulk, which lies between a lower and an upper limit, depending on the amount of data you have. And then depending on whether you're over-parameterized or not, it also will have this spike. So delta function at the origin of eigenvalues that are exactly 0. Okay, so with this tool, we can now compute the average training dynamics in this situation as a function of the amount of data you get. So let's start off over here. In this case, you have twice as many examples as parameters. There's the Marsenko-Pasteur distribution just has this bulk, and you can see that the smallest non-zero eigenvalue is well separated from 0. There's a little gap here. And that means that overtraining is going to happen, but it's not so bad. You don't have really small eigenvalues. And then jumping over to this case where you have very little data, now you also have this bulk that's well separated from 0, but you have a delta function spike. The delta function spike is going to incur constant error, but again, you're still not going to get substantial overtraining because the gap between the smallest eigenvalue and 0 is still appreciable. So the only time things really go badly is when alpha is exactly equal to 1. And then the Marsenko-Pasteur distribution snaps up towards the origin, it's converging. This means you have lots of really teeny eigenvalues, and that is catastrophically bad because they're showing up again in the denominator. Right? And so this network, in fact, will overtrain indefinitely. It just keeps increasing. And just to show you this a little more systematically, so if you plot this as a function of alpha, you can see again that there's this big spike if you train for long times around alpha equals 1. So the observation was initially surprising to people is things get better if you go either direction, right? Make the model smaller or larger.
So, yeah, so I believe some of the students will recognize the Misha Belkin reference. And do you want to talk about the relationship between your work and his?
Yeah, so I think essentially so I've looked at this very specific case, and frankly other people have before me. And in fact, the papers after my paper came out, looking at this exact same model again, so sort of they rediscovered it several times. And Misha Belkin's point is really saying that this phenomenon holds generally, right? So this is not about the linear regression case, and he's done a very nice job of laying that out, showing the kernel machines do it. It's not specific to neural networks. General point about these learning systems. And this is, yeah, so right, so people call this the double descent curve, and I think it's a good name for it. And I think the intuition is basically that if you're in this over-parameterized regime, and eventually you're going to get zero error. And once you do, you're not going to train anymore. So there is a natural end to the training process in these models. And that's very generic. It's not specific to neural networks. Yeah?
Can you give some intuition why in the alpha equal 1 case the magical factorial distribution looks so different?
That's a great question. I mean, I think the short answer is no. I still struggle with some of the intuition here, but I mean, I don't know how useful this is, but just it's not like it's an instantaneous flip. So if you do imagine like this peak, right, it's just growing up towards the corner, and then eventually it snaps up to the origin. Okay. So again, I just want to highlight.
Well, I mean, there is a way to understand it, which is alpha equals 1 is a square matrix, and the square matrix is it's just barely going to give you a determined system, just barely, right? If you took away one equation, it wouldn't, etc., right? So you understand that it's critical, it's unusual, and the exact form that he's showing you is just what he said. You've got a lot of singular values close to zero. Like the smallest one relative to the largest is like 1 over square root of n for an n by n matrix. Now, if you go on the other side of that, so these matrices have the form that their transpose has essentially the same singular values as the original matrix, except they might have a bunch of zeros appended. So once you go into the underdetermined case, its transpose would be plenty well determined and would not have small singular values. And so what happens, you have a bunch of exact zeros where nothing is ever going to move, and then you have a bunch of things that are far away from zero and are never going to cause any blow up on division. Which is what his graphs are showing.
Yeah.
The reason the graphs are like that is because of these relationships between singular values of matrices and their transposes.
Another point that you can maybe see intuition is, so why is this gap between the smallest non-zero eigenvalue growing as you get less and less data? Well, suppose you have the limit of just one data example. Okay, well then clearly almost all the directions you have exact zeros. And then in the direction of that one data example, you have the norm of the data example. It's actually a big number, right? Because you have lots of inputs, so it's highly concentrated at its norm. Okay, any other questions? All right, yeah, so just to sort of highlight in the shallow case, the two properties that are sort of allowing things to work all right. The first is this frozen subspace, so if you have a small amount of data, at least you are not undergoing dynamics in the directions you don't have data in. So that's one important effect. And I think the other important effect is this eigengap phenomenon. So the lower edge of the bulk actually moves away, gets larger, moves away from zero as the underparameterization gets more extreme. And again, the intuition is sort of what I just mentioned. If you're right here, then basically what you're getting is just one example, and minimum eigenvalue is the norm of that example, which is 1 in the way that we've normalized it. All right. So there's some other features of this setting that I think are important to point out. One of them is that there's a strong impact of initial weight norm again. So if you are in the regime where you don't have much data, you have this frozen subspace, whatever you put there sits there forever. But when you're evaluating testing error, new test examples can come in that subspace and affect your generalization performance. And so here I'm plotting the testing error as a function of different initial weight norms. You can see that only for the alphas less than 1, you see a very strong dependence in performance on the initialization. So that's saying that if you're in this high-dimensional regime, you need somewhat small initial weights as part of your strategy for getting good performance. And again, it can be a little abstract, so I just want to say, like, here is what that looks like with that sinusoid example. Part of what I did when I showed you this is I started off the weights to be very small. If I had just started them off with large weights, then it doesn't look as good. Right? So it's saying part of the implicit regularization really was coming from how you initialize these models. Another simple phenomenon to point out is early stopping. So this big spike in test error, it's if you train for a really long time, but you're not obligated to. And so if you just early stop, then the curve looks like this. It's very well behaved. And so I think what that's saying is pretty much you don't need to worry about overtraining. Because like even when it's happening, you can just stop training early as long as you're monitoring a validation set of some kind, and it doesn't look like it's really impacting your performance too much. You can compare this, by the way, to the optimal regularization, and at least for the setting I'm examining, early stopping is exceedingly close to the optimal regularization for this problem. Okay, and finally, everything I was talking about was shallow networks, so does this hold at all in more complex neural networks? You should definitely ask this question. Here's an example where I've just made the teacher and the student now nonlinear. And for this model, again, in the green curve here, we have the test performance. You can see a large spike around where the number of parameters is equal to the number of examples, and then things get better in either direction you go. So this is just, again, the double descent phenomenon that has been, that we were just talking about. And if you early stop, that's in the blue curve, you can see that things just get better and better and better. And in fact, the largest models are the best models to be trained. So one thing we can do in this network to see if this sort of view of the Prosecco-Pasteur distribution is relevant is we can just look at the covariance spectrum in the film layer. And things change, but it does seem qualitatively similar. So here, again, in the over-parameterized regime, you have, this is in the regime where you have lots of data, and you see a little gap between the small sign value and 0. Here in the over-parameterized regime, again, there's a gap, but you have a delta function spike. It's maybe hard to see, but there's one there. And then things are really bad when you're exactly matched to another data you have. And finally, if you have a lot of GPUs, which I don't, but luckily this group did, then you can do this experiment on full-scale models and show indeed this insight holds on these full-scale, appears to hold on these full-scale models. And I just want to emphasize, this is kind of surprising when you first see it. What this is saying is there are regimes where adding more data to your problem makes the model do worse. Right? It's kind of a funny property. But again, if you early stop, you would be fine. Okay, I think I will. Okay, well, I'm going to very briefly talk about these things. So this simple model lets you, I think, get some insight into some other proposals for how to think about generalization. So one popular idea is to say, maybe stochasticity can regularize your solution. So maybe what you should do is do gradient descent, but then add noise to the gradient as you're doing the updates. But if you think about this frozen subspace, what that's going to do is in the frozen subspace, you will start random walking, and the norm will grow and grow. And so, in fact, you have diverging test error in that setting. You also might think that what matters is how far you've moved from where you initialize. But again, you can construct examples where you might be far away in the solution subspace, or sorry, close in the data subspace, but far away in this data null space, and you would still have large test error. I think it's a useful model for thinking through some of these things. There's another fun example of this. The null space weights are zero mean. So what this means is if you ensembled a lot of repeat training, you would average out their effect. And so in this simple linear model, ensembling really does help, and this is also demonstrated. And a final point that I find intriguing here is if you consider this question whether sharp minima generalize well. Well, in linear regression, which is what we're talking about, the Hessian is just the input correlations. So what this means is that all of the minima are equally sharp, right? Even though they could generalize very differently. And intuition is that this frozen subspace is a totally flat direction for the training error. It's not about the training error, right? What you care about is the variability in the data null space, which can cause these different test performance measures. All right, so to summarize this picture emerging from linear models, generalization can be okay in these large networks, even with infinite training time, field batch gradient descent. And I think that's because of interaction of a lot of properties. So the explanation that I put forward relied on the algorithm that applied just gradient descent. It relied on the data. I made a strong assumption about the teacher. You know, for instance, that sigmoid, I could have connected those 10 points with any curve I wanted to, right? I'm sorry, the sinusoidal example, I could have connected those points with any curve I wanted to. But I didn't. I used the sine wave, which may be a simple connection to those points in some sense. So that also featured. And then there are model properties, for instance, starting these models with small weights. And I just want to say that bigger is not always better. So it could be that a larger model does worse than a smaller model, and that seems to be dependent on the noise properties. And then once we go to the nonlinear case, a lot of the results I've been showing you, basically early stopping is really good because it's close to L2 regularization, but that may not be the right thing in nonlinear networks and in deeper networks. And if you're interested in some nice related work that's much more formal and precise than what we originally put up, then you can see this recent paper, which has a bunch of other extensions as well. Okay. So the final thing I'd like to do is try to push these two parts that I've been talking about together. So in the first part of the talk, I've told you that you need large weights in order to train quickly. And in the second part of the talk, I said you need small weights in order to generalize well. So if you put those two together, it suggests that in fact there would be a speed accuracy trade-off in these vanilla deep networks. And in fact, there does seem to be. So for instance, on the left-hand side, if I make my weights really small, you can see this network gets stuck for a long time on a plateau-like phenomenon, like the ones we're talking about, before it finally gets to a lower training error. But then if we go over to the test loss, you can see that in fact, it's the one that does the best out of all of the loss. So you sort of have this choice to make. Do you want to train fast, or do you want to generalize well? And I think this sort of makes the broader point that here's an example using CFAR10 in a convolutional network, just to see if these ideas generalize. And again, you can see that these small initializations are taking a long time to train, but they are the best performing ones. And it's making the point that an initialization prescription that was designed to optimize training error is not necessarily the one that optimizes generalization error, right? Which is probably what you ultimately care about. And finally, so these were all with pure gradient descent, no fancy tricks. But we have started looking at more complex architectures. This is a network with batch norm, a residual network with batch norm. And now it looks like the trade-off no longer exists. So it's you train faster and you generalize better if you start with smaller weights. I find these things intriguing, and it's, hopefully at some point we can understand how this is arising in these more complex networks. But one just thing to note here is sort of the standard initialization prescription. The he et al. Initialization corresponds to this curve. So you could have made this network for free perform much better just by cutting your weight scale by a factor of 10. And it doesn't even take longer to train. So it's quite an interesting example of the initialization dependence in these architectures. All right, so I guess just to wrap up, I've shown The depth itself causes some of these rich dynamical phenomena, like these stage-like transitions and plateaus. I think the message emerging from the generalization section is that I really don't see a way to get around having to consider the data, the algorithm, and the architecture together. So I'm not sure we're going to find ways that don't involve analysis of all of these elements. And I've given a simple sort of step in this direction. And I think for the future, I find it quite intriguing that the deep dynamics depend really explicitly on what's already in the network. Right? So I've been talking about these simple solutions from starting from nothing, small weights. But of course, you could have started from rich training on previous tasks, for instance, the continual learning setting. And there's still much more that we can learn from these models. All right. And with that, I think I'll conclude. I just want to acknowledge my collaborators here. So the generalization piece was done with Madhu Asrani and Yamini Bansal. And the training error piece was done with my advisors here, James McClelland and Cecilia Bailey. Thank you.
What matters is the eigenvalue of the solution. These are directions that are supposed to be correct. I wonder if you have something similar to say about nonlinear networks. What is the equivalent of the eigenvalue there? Is relevant when you don't?
Yeah, that's the question. I mean, I wish I had an answer, but I just don't. And yeah, I think there could be ways forward there, but I doubt it would be a generic answer. Right? I mean, if I could answer that for any nonlinearity and for any problem, then we would have solved an extremely difficult problem. So my suspicion is not to start from the simple special cases. One that I've been thinking about is, suppose you just have a few linear models which you switch between depending on what the example is. That's a simple version of nonlinearity that I think you could get an analysis of.
Kind of going off that question, part of Dr. Pennington's lecture is he considered very wide nets with general nonlinearities, and they derive, use the limit theorem, they derive something that's kind of tractable, and he derived some dynamics in one of his papers that has the same sort of features I taught of a matrix exponential. And that matrix exponential evolves over time to eventually converge to something. And I think that dynamics emerges from the exponential in time, and that particular matrix was the neural tangent kernel. And I was just wondering, within this case of pure linear networks, isn't that just actually exactly the data covariance matrix?
Yeah, so this is a great, it's a great point. So the neural tangent kernel and those methods, they're starting in a particular initialization regime. And it's in the regime of these wide networks initialized with actually quite large weights. And that to map it back to the linear part, you won't see these plateaus and stage transitions if you apply those results to these linear models. What you get is something much more like a shallow network that's learning with essentially exponential learning curves. And that means that the inductive bias is different. So the results that I've shown you starting from really small weights would be what they call the feature learning regime. And in the linear case, you have essentially a low rank constraint, is the implicit regularization. Whereas in the neural tangent kernel, you get this more like a minimum L2, sort of L2-like regularization constraint. So I think those results are really powerful. I just want to point out that the fact that the tangent kernel changes is sort of key, I think, in getting some of these more complex phenomena to come out.
So Andrew, I have some questions slightly from Canvas, and so this is part of a grading system. If you don't mind, could you answer the following two questions I selected?
Okay. The question is, in your linear models, how does explicit regularization compare with early stopping and preventing the overfitting regime? Okay, good question. So For the case I'm talking about, L2 regularization is known to be optimal, and the optimal regularization parameter is just 1 over the signal-to-noise ratio for this particular problem. And if you compare that to early stopping, it's slightly different. Like we saw differences in like 3% relative error, but they're almost on top of each other. I'm not sure if I have this slide. Yeah, it looks like I don't have the backup slide, but it is in the paper, a direct comparison. Essentially, for this task, they're nearly indistinguishable, but that would not hold if it was a nonlinear network or had more layers. And second question is, what is the biggest barrier to integrating deep learning with psychology? Oh. What is the most effective or exciting application to the field of psychology that you have observed? Well, maybe one thing I'll just say is deep learning has been integrated with psychology for like 20 years or more. So deep neural networks were arguably originally studied in psychology departments as well. So I don't know if you're familiar with James McClellan, who's in the psychology department here, but his book on parallel distributed processing kicked off a lot of interest in neural networks. So it's actually been a very long-term effort. And some of those applications, I don't know if this is the most effective or exciting one, I'll just tell you one that I was involved with. So I talk about these stage-like transitions. If you expose a network to hierarchically structured data, then in fact you will get one stage for each level of the hierarchy. And depending on the correlation structure coming from the hierarchy, it will start with the broadest distinctions, then go to so like animal versus plant, then go to dog versus cat, and so on down the tree. And that pattern of, they call it progressive differentiation, so starting at the top and going through these quasi-stage-like transitions, is exactly one of the empirical observations about childhood development. So developmental psychologists have measured these types of learning curves, and in fact, it is the case that children first learn broad distinctions before they learn finer ones. So that's just one example of how I think these phenomena can be put together.
Okay, a few more questions.
Yeah, I'm not sure if this question is off the wall since I already mentioned psychology. Like in human learning or like adaptation, the natural system we always see punctuated equilibrium, and means it stayed on some kind of they're very slow dynamics and they change dramatically. What kind of dynamic analysis can you apply, and what can you say about this kind of phenomenon? What is a local stability that's happening in this type of system that we observe in nature?
I'm not sure. So are you saying that the training experience actually changes over time in different?
Yeah, it just seems to not be a stable minimum in the dynamics. It seems to be always changing when going through periods of slow dynamics.
Yeah, right. Yeah, I'm not sure. I mean, so maybe one thing to say is everything I've talked about, you just have a static environment. The statistics are always the same.
Right.
And really, of course, we have curricula. We go through changing environments. So it would be very interesting to redo this with changing environments. And I don't know of any work that's done that explicitly with this. But in the case of static environment, then these equilibria are really just, you've learned some number of these saddle points, but you're still stuck at another number of those saddle points and waiting to eventually expel. Yeah.
So just curious, when the depth goes to infinity, like what would be that scenario? Would it be like linear regression again?
When the depth goes to infinity, it depends on the initialization. Yeah. So if you initialize with orthogonal weights, then pretty much it's like linear regression. I imagine that all of your weight matrices are relatively large, and you're just learning, just think of it as a bunch of random transformations of the data that preserve all in one. And then you just learn that last layer. So yeah, it is kind of like a shallow dynamic. I didn't really show you that, but that is true. But the other regime is you have infinite number of layers, but you initialize them with small weights, in which case the situation is very different. If you could train for a really long time, you would eventually get a low rank solution, but it would take very long.
So I have a question about the validity of the analysis of the training runs of deep linear networks. So basically, aside from initialization, essentially what you are doing is actually that you are decoupling some modes, and in order to do that, you would need an initialization that somehow align the initial weight value factor. And one way to think about that is to think about it as random initialization but with a very small value, so close to zero. But at the same time, you are saying that you need a big value so that you can basically have faster training speed. And so, do you have any quantitative statement on how big and how small it is, so that at the same time you can keep your analysis degree and valid, and also the training speed to be fast enough?
Yeah, it's a good question. No is the answer. So, it's something that I should have done probably long ago, but I haven't examined how quickly the decoupling happens. But, I just observed that empirically. And then as the weights get larger, the decoupling plays a stronger, the decoupling dynamics play stronger and stronger roles, and you really can't ignore them. Yeah, so once you have large weights, that kind of is the dynamics rather than what I've been describing. And the exact transition between those two, I haven't analyzed quantitatively.
So one application of random matrix theory is just analyzing how robust your estimators are in the way that you're training data. So I'm wondering if there's any results that you have about how depth affects robustness to actual noise in your training data rather than controversial noise.
Yeah. I know that slide. Okay, so you could imagine saying that the way your data was generated was there was some real category structure. So a low rank matrix was your input, but then you don't observe that. You observe that plus noise. And then since you know you're going to recover the singular value decomposition, that's a known function, right? So low rank plus noise, we know what's going to happen. And then you can calculate the recovery of the correct underlying category structure as a function of the parameters of that setup. Yeah, so we have done that for at least that simple case.
And so does depth sort of come in at all into the picture of how robust you are, or does it not really?
No, the only big difference is, do you have one hidden layer? So it's one or more, you basically get the same thing. But that, I think, is, yeah, there are a bunch of simplifying assumptions we're using. That could change, for instance, if you weren't starting with small weights. And the other thing, which I didn't really highlight, is I'm always, in most of what I've been talking about, considering a case when the input correlations are white. And so that's another case where these two things might diverge. I haven't looked into it. Yeah.
If there's no further questions, let's thank our speaker.